Okay, so the third session of today's Creators Track, it's called Immersive Technologies from Capture to XR Experiences. So we'll basically learn about the influence XR has on the media industry. And our speakers today are Valerie, Allie, the Video Solutions Group Director at InterDigital, and Christiaan Varekamp, who is a senior scientist doing research at Philips Group Innovation. So give it up for our speakers.
Thank you. So, hi, I'm Valerie Allie. I'm leading the InterDigital Video Solution Group within our research and innovation organization. I'm pleased to share today this session with Chris on immersive technologies from capture to XR experiences. So, InterDigital business model is rooted in research and innovation. Our world-class engineers develop advanced technologies and contribute to global standards to define the future of wireless communication and video. So let's start with some keywords around industry trends towards immersive, sensorial, interactive experiences. To do that, I just thought and just pick up some hottest topics. This conference tracks. What do we talk during this event at AWE? We talked about collaboration, training, education, healthcare, wellness, retail, e-commerce, advertising, and also gaming, entertainment, and media. All that, when you start to think about collaboration, remote learning, it's about telelearning. It's about moving from remote learning to co-presence, feeling the presence, feeling to be at the same place of the others. And when we talk about that, the key elements, when we talk about telelearning, for instance, or co-presence, today we are manipulating 2D videos. And we do feel that we need to go one step further. We need volumetric video. We need natural viewing. We need natural sense of depth, parallax. So we really need to be in the real world. And we want to move from this 2D to volumetric to metaverse. And where with metaverse, we will have a complete scene, a complete environment with different type of media we want to interact with. So it's about also interactions. It's about sensorial experiences. Again, to really bring natural experiences. And again, last point with natural experiences is about real video captures, live experiences. And about all these keywords, let's say, InterDigital and Philips contribute with open standards and enabling technologies for large-scale and interoperable XR experiences with real content. It's really the key point for us to provide the tools to the industry to distribute such type of experiences at large scale. And we will go through different topics today. First is about volumetric video streaming and rendering at large scale, is about sensorial and interactive experiences, and volumetric video creation pipelines. So let's start with the MPEG-V3C immersive codec. MPEG-V3C stands for Visual Volumetric Video-based Codec. It's an MPEG standard to enable volumetric video efficient streaming and rendering. What do we call about volumetric video? For sure, here people know about volumetric video. It's a video in which the user viewpoint can be viewed dynamically updated. It's really about natural viewing, having the sense of depth, the sense of parallax. So for that, we can have different ways to capture volumetric video. We can have the viewer relatively close to an object or a group of persons, and he wants to watch all around them from all the sides. So for that, we will have conversion rig acquisition, and we'll use video-based point cloud content. So it's about point cloud content. And we can also consider the viewer relatively far from the scene and having the full scene in front of him, and also wanted to have this parallax effect. As I'm naturally moving in front of you, I get some sense of volumetric information. And I want to get that also from the video I'm receiving and on my XR experience. This is the two type of contents we want to handle with these new standards. So with dynamic point cloud, So we do have a set of points in the space where we will get the geometry, we'll get the texture. And on multi-view plus depths, we will also have multiple cameras acquiring this information, and we will have depth information. And the depth information on real content will be mainly estimated by photogrammetry. So we'll create some artifacts, spatial and temporal artifacts. All those data require significant bandwidth. And we want to distribute such data which are quite heavy. So that's where compression is crucial to achieve sustainable data rates. So for that, we have this MPEG-V3C standards. And the MPEG-V3C standard is the video-based solution. That means that we leverage 2D video compression schemes like HEVC codecs, which are really efficient in compression. And we use them to really be able to reach this goal of sustainable data rates. For that, we use as an input this 3D content, point cloud or multi-view, and then we create single 2D streams, texture, geometry streams, transparency streams, and we use the 2D codecs to deliver them. On the receiver side, we are able to recover all this information and create the virtual view locally on the device. And this is what we are implementing and we are showcasing today at AWE, is this core compression elements going from volumetric capture pre-recorded to any type of rendering device with VR or AR use cases. And we do that in partnerships. So we want to stress here our InterDigital and Philips research collaboration to promote this MPEG-V3C immersive codec. And we work also with external partners. We are open to work with any external partner, providing this tool to the industry. And I want you to name here XD Production and Volograms, who are providing us with point cloud data as an input data. And it's important to provide those tools to the industry so that if you create such volumetric contents, you have the tool to distribute them at scale and in an interoperable manner. And for that, we have this decoder platform, where finally what we have here, what we have here is a Unity plugin inside a Unity environment where we are able to decode all this volumetric information and render to the different end devices, whether it's smartphones, tablets, or headsets. And that's really the first implementation that is showcased here in the industry that is able to manage any type of input data, whether it's point cloud or multi-view plus depth information. So the objective also of InterDigital is to bring additional all the elements or the dimensions of immersive experiences and also be able to stream all this information, again, to really be able to deploy an immersive experience at large scale. So for that, we want to work on haptics. We want to add to this sense of depth and sense of parallax, we want to add a sense of touch, because touch is fundamental to perceive and understanding the world. So for that, we need to work with haptic information. And why do we need standards also for that? Today, on the authoring tool, when you create assets, you can sense haptics information or you can create haptic information that we want to deliver. On the other side, you have rendering devices where you are able to render these haptic effects with haptic actuators. But as 2D content, as video content, if you want to distribute at scale, you need to have a standards to define what is the format of those information. And that's what we do with MPEG Haptics. So with MPEG Haptics, we are able, when we stream an experience, to deliver the video content, the audio content, and the haptic content, and be able to have this haptic information synchronized with the video content. So on top of that, it's about scene description. When we talk about a large scene, experiments, you want to be in a full 3D environment where you want to to build these full environments, be able to have different type of media, interactions. You want to handle with video, you want to handle with avatar, you want to have haptic information interactions. You need to have scene descriptions in order to synchronize this type of XR experiences among multiple users. And for that, you have existing standards like GLTF who provide this type of tools. In MPEG, we want to extend that, again, to be able to handle time media information, haptic information, and really bring all this interactive XR experience. What we showcase this year at AWE are two gaming applications where we leverage the use of those standards. So you can experiment a game, an haptic game, with this haptic information. So there is an interactive game with using the scene description information where we gather the haptic codec information to provide you with all this sensorial feeling. So that's something that you can experiment on our booth. And on the scene description level here, you have also a multiplayer game where you do exploit all this scene description information. You can have interactivity, and you can also you are also able to handle with interactive media and with point cloud information. So all that is really to show, in fact, the objectives that we have here is really to show and to provide tools to the industry to be able, from all the content, immersive elements that you have to create your immersive experience, to be able to distribute largely at large scale in an efficient manner and in an interoperable manner. So now I let the floor to Chris on this volumetric capture pipeline.
Yeah, thank you very much. So if you think about the capture side, these days we use laptops, phones with built-in cameras, and that just works. And on the other extreme, we have let's say the film industry that has complicated setups. For 6DoF, we want easy setups. So we've split in our work the attention to two pipelines, one for sports and media and one for telepresence. I think those are two big applications. So I'll first talk about the sports and media pipeline, but before I do that, I'll introduce Philips shortly. So IPNS, Philips Intellectual Property and Standards Division of Philips, supports innovation and opportunities for third parties, as well as for the own business, obviously. It's part of Royal Philips, and Royal Philips is in the medical domain. In the IP portfolio in 2022 is 56,000 patent rights. That's quite a lot. And there were 920 new patent filings in 2022. So this is a setup that we built for immersive sports. You saw the camera rig now, and this is one camera feed. And what we can do is from a normal camera array, without a specific background, we can interact with the content, as you can see. So the idea is here that you play it on a phone or on a headset or on a 3D display agnostic. And we can even edit objects out in real time. So this is a WebGL player that runs also on a headset and on a phone. And we can start again. So this is basically the switching between two modes of operation. So how does this work? Yeah, it works there. So on the left we have the capture side. Calibration, conversion, transmission, and rendering. This part is the MPEG standards. So here we start with, for instance, this capture setup, and we have to auto-calibrate. Intrinsic calibration is given, for instance, for these cameras. Extrinsic calibration we do automatically. And then we calibrate the scene. And we do that by fitting planes on the surface of the field and in the background. We pass some metadata, and this is the main conversion pipeline. So it's a multi-camera capture, undistortion, object detection with neural networks, then a depth estimation, and another segmentation path. This segmentation path segments out objects in terms of depth. We extract patches, extract the background, and we generate a single 4K or 8K atlas. So this contains all the information you need, packed together in small patches with metadata. That goes to the client side, and the renderer binds the depth patches on depth back to front order synthesis and blend and composite, and we have the demo that I just showed. These are some examples of typical setups. The outdoor setup you already saw, this one. This is a typical indoor setup. You can imagine that you can mount these types of machine vision cameras in the infrastructure of a soccer match or a baseball match or a boxing match and automatically calibrate and stream. Here's the rigs and the cameras again. Now, to go into a little bit more detail of the conversion pipeline, just here before or after the object instance segmentation, we have an important step. It's called depth estimation. This is multi-view depth estimation. That means that we have to do temporally consistent and view consistent depth estimation. This is a non-trivial step. After that, if this works out right, we can do a depth segmentation. And here it's important to have consistency over time. So these colored objects, let's say depth segments, I would call them, they have to remain the same label over time. And the reason for that is that we have to feed them into the codec, and the codec needs to be temporally consistent. Otherwise, your bitrate flies up, because at the same time you do pixel rate reduction. So important for the depth estimation is that it's conditioned on the scene, and it can handle noisy patches. It's robust for occlusion and accurate at boundaries, and for depth segmentation, it's important to create the patches appropriately for coding and rendering, and we have to create a background sprite, and the patches has to be label consistent. Now this is then an outdoor scene, an example that we captured. So on a headset, you can really walk between the players, and we see that it's quite an interesting application. Now, another pipeline is intended for telepresence. Imagine that you're looking over the shoulder of an instructor or someone that is doing an operation, or you're just doing a video call. How can you do this on a normal screen, a 3D screen, or the 3D headset? Pipeline that we're looking at here is as follows. Again, capture, calibration, conversion, transmission, and rendering. Here is a typical setup. A 2D laptop, a 3D laptop with a 3D screen. In this case, a Dymenco screen, but you could have another 3D screen, or you could have a headset. Again, here, intrinsic calibration, device extrinsic calibration. For instance, for the Azure Kinect, you get these data, but you may have to re-estimate. This self-calibration is an important step because it has to be stable, the setup. If you have a small accessory as a device that you plug in your laptop, if you touch it and the rotation changes 1/20th of a degree, you're out of, you have a problem. Again, some metadata. Oh, but let's go back. And here we have the conversion pipeline. Multi-view capture, undistortion again, depth warping, trimap generation. Here basically isolate the pixels that have to be alpha matted, alpha estimation, depth extrapolation, and packing. Again, an interface format. Images, in this case, a very simple atlas. Live transmission, and then again, a rendering pipeline. View synthesis, stitching, and texture hole filling. This is a setup that we built. So here you see some examples. This is for a standing experience. So you have an array of cameras at eye level almost, a vertical field-oriented field of view, and you can capture a person that is presenting. Here a similar setup, and here the small setup that we're demoing here at the show. Some details again. This time about the extrinsics calibration. One of the problems with the setup is that if you have estimated intrinsics and extrinsics within the device, you're not done. You have to estimate the extrinsics between the different sensors. And of course, the distance can be, for instance, 50 centimeters. So there's some flex in the mechanical structure, and that's a problem. So you have to do online calibration. And that works as follows. We have the images. We do traditional structure for motion, estimate rotation and translation up to scale. And then we have a module. This is a depth-based scale estimation. So we estimate a single parameter, the scale parameter S. So this is almost trivial, but this has to go right. So if we have the extrinsics between the cameras calibrated, we can go again into the conversion pipeline. And that works as follows. We capture images, in this case 4, undistort them, depth warping from the depth to the image, and then trimate generation, alpha estimation, and depth extrapolation in the uncertain region, and packing in the atlas again. So here's an illustration how this works. This is the first camera in the setup. This is the second camera device in the setup. Both have a color sensor and a depth sensor. Then if we have an intermediate viewpoint, it can be in front, to the left side, in the viewing zone, and we directly split the points to the viewpoint, you get something like this, with little holes, big holes. Same here for the other anchor. Then for the new viewpoint, this one here, we can stitch them together. Still we have missing points. Then there's an important step, that's the texture hole filling. This one takes care either with a fixed filter or with a pre-trained neural network. Mind you, it has to run on the client. It has to be very efficient in the target view. We fuse those two predictions. This is a demonstration of how that will look like on a 2D laptop. So obviously you can't see 3D. On our show, we have a 3D laptop that shows how this works. If you know the together mode in Teams, this could be the next thing where you place people around a common table, put on a headset and be part of that meeting, or on your, let's say on your, let's go back. Go back again. Yeah, play it again. Yeah, this place. So again, this is central view and then around the table. Obviously, there's lots to do here that have to do with details on how you render it. But you can imagine having multiple people around that. So I think I'm roughly on time, and I'd like to finish with this slide. So please visit our booth if you want the live demos and if you want to get more information on how you encode all these types of data and what choices you have there. Thank you very much.